different embedded real-time operating systems, and Hubris is one of them. It's not really a real-time operating system, though I think you can use it as such in a pinch, but it doesn't have any specific features traditionally found there. It's these microcontrollers typically have no MMUs, but Hubris requires memory protection units. Why? Because it uses memory protection for secure task separation. In a typical, let me see if I can get out of this. I guess I need to show it. If we have a, if we can look at a typical part datasheet for, no, it's worse. It's worse than full screen, you know. Let us see. Like that. We have, yeah, you can see memory protection unit. It's a thing specifically meant for embedded operating systems to do exactly this feature with memory protection for segregated tasks running in memory. It's from security perspective. I'm really not a security guy, but you know, it's not the same security picture as with a general operating system. There's it's more a case of to protect each other from accidentally ramming over each other independent tasks than some malicious hack. Though it also can be a case if it's a networked device or if you have some form of physical access to it. But original domain for the company is Oxide that develops it. They also develop some solutions in co-host in collocation area, and one of these main motivation, as I understand, was programming board management controllers. It's a chip typically found on the main board and a part of IPMI subsystem, which allows you remote management of devices. Like you remember this famous discovery when it turned out that Minix was the most popular operating system in the world. It was running as part of IPMI on Intel products, and that's exactly that. They don't want Minix there, so they have their own system that allows to simplify it, make it more secure, because BMC is exactly the place where, which is really important from security perspective, especially if it's a collocation system, some sort of shared solution. So yeah, how a typical deliverable system in Hubris is organized. It's split as say in the tasks. Each task is a separate compilation unit. It's written in Rust, by the way. So each is its own Rust compiled unit. Tasks, when executed, are ranked by priority. It's just a numerical value determining relative priority over other. In microcontrollers, you don't really have any priority rings or any sort of hardware priority control mechanism, so it's purely handled by the operating system. It runs on protected memory regions, leveraging the hardware on microcontroller. That restricts a bit what kind of microcontrollers you can use for this operating system. Right now, most of examples there I think I've seen is ARM parts, Cortex-M microcontrollers, and there are really they're also looking at RISC-V from what I see in documentation, and but there isn't really much in the source tree on it yet. Probably doing what they have to do for actual business for production. So tasks communicate via message passing. So it's completely synchronous interaction. They have no queue. That certainly simplifies implementation and gets you let you get away from runtime allocation. So Hubris is not big on any sort of runtime allocated data structure. You sort of have to plan in every module, in every task. You have to plan your memory beforehand. So yeah, each task is associated with a generation counter, which is really more a reincarnation counter, because a task, even a task written in Rust apparently, can fail, and when it fails, the generation counter increases, and that helps both for debugging purposes and for message passing. It allows to see when the task that communicated to you and the task that replies to you was actually another instance of the task, to avoid integrity issues in processing. Hubris does preemptive scheduling, but it's not the kind you typically would expect from BSD or Linux or some normal general operation system. It doesn't do time slicing. So it's not hard preemption. Instead, what happens, since the programs block, they preempt only when a higher priority task, when higher priority task is released by some condition, it gets message, for example, then it preempts to a higher priority task. So that naturally is that if all you have, say all the tasks assigned the same priority, you get the classic cooperative implementation. So that again simplifies implementation, makes programming a bit more difficult. There are timers, of course, in the system, just that there is no time slicing, there is no this typical preemption as we know it. Let's see. Yes, and the set of tasks is determined on compile time. You don't just suddenly start spin out more tasks when the system is run. It's configured in an application description file that we'll get back later to. IPC, as I mentioned, it's synchronous messages with chunks of quarter kilobyte blocks, which isn't really that useful if you have some high throughput or signal processing application. So that's why they also provide memory releases, feature probably inspired by Rust itself, when you lease and borrow stuff around, and you can allocate memory, not allocate, you can designate memory in one task and pass a sort of descriptor to it with a message to another task. Then that task can read or write that memory depending on permissions, and notify you when it's done. Because when you do this part with synchronous message exchange, you can send a message and you can expect a reply to that message from a task when it's done. That's how tasks get stopped and restarted. They block on when they send message, they get continued when they receive the reply. And additionally, you have a mechanism for notifications, just simple numeric table of notifications that are sent and listened to by other subsystems. So in a blocking call to like send receive, you can also add a notification, how would say, list, notification mask, that would also allow you to unblock on this notifications, which are really implemented over system interrupts. Ja.
Så de meldingene, det på en måte bare, det som om det skulle vært et kall. Det bare alltid en melding, eller det kan på en måte være en stekk med meldinger.
Stekk?
Ja, altså det som et funksjonskall. Å sende en melding, i og med at du ikke har en kø.
Ja, det är ingen kö. Ja, det blockar dig för den andra task. För den andra task blir utförd när det får scheduled och där det får chans att behandla och svara dig. Eller hvis det dör där du får en sån viss speciell värdighet.
Ja, okej. Så hvis du sender en melding så blir du blockad.
Ja.
Men det är inte nödvändigtvis den som mottar meldingen som får köretid. Det kan vara något annat. Eller?
Ja, du får reply normalt från motparten. Så,
men det är den du sänder melding till som får köretid?
Köretid?
Ja.
Nej, timeout menar du?
Yeah. There's a scheduling system, right?
Mm?
So when process A calls into process B in the system, at the time when process A does the call, it has the CPU.
Yeah.
So and then you make a call, and then the question is.
Yeah, when you make a call, you block, so you yield sort of.
Yeah, exactly.
So,
but it's not automatically necessarily the process that you're calling into that will continue execution at that point.
No. When the process is scheduled and it gets. Yeah, so it's not really. It looks like a function call, but it's not really a function call. So,
right.
Yeah.
Do you also is there a sort of return facility? So is that sort of a 256 byte buffer that's being sent to the?
That's a great question. We can have a look. Response codes and result. I think sending messages. So yeah, leases I think is for memory lease.
Sent in response will the buffer. Right. Okay.
Yeah.
Is there any upper limit on the size of that?
Of
The response, the incoming. It just says it's a mutual array of U8, but could it be a megabyte?
No, I don't think so. I'm pretty sure it was 256 bytes, but
so it would make sense. Okay.
But yeah, so you can have a return buffer clearly, since there is a length deposited. So message size limits. To limit, we impose maximum length of messages 256 bytes, and they rationalize it as avoiding not deadlocks, but avoiding poor interrupt performance, because that's this whole thing operates basically by interrupts, as it's So let us see. We'll have a peek at the code, but I should mention first the debugger. Hubris comes with humility. It's interactive debugger, but it's I guess it started as debugger, but it sort of merges in itself the OCD interface, and it's also not quite a linker, but a programming tool, and also sort of features you typically find in bootloaders, like in U-boot, where you can probe different devices and do small things. It's sort of organically grown debugger with features that you can clearly see related to what exactly these people do who develop it. So there's a lot of commands, but some of them are generic, some of them are really kind of hardware specific for specific versions of systems. So yeah, it can do probing, arrays, and flashing. It can give you a core dump from the system that you can do a post-mortem work on just as well as on the live system. You can inspect different aspects of the systems and manipulate devices if the system supports them. And you can manage tasks. make them halt on failure, stuff like that. Inspect stack again, inspect system variables.
So connecting the debugger, is that like via GPIO, I2C, or
Yeah.
it has a bunch of different
That's
applications?
that we should get to. I think it's demo time. I have a blister pack with a board. It's not quite the board they use, so I'm not sure they have 100% support of it, but it worked last time I touched it. It's a STM32F4 Nucleo board, but not the kind Nucleo they have in board description files. So I'm going to use a different file. Let us see. The text is too small, I guess.
Contrast is a bit up in you.
Let me see.
Maybe non-comment text is fine.
Yeah,
maybe
it's probably just clear comments and use it from there.
Here?
Yeah.
How do you increase here? Oh, wow. Yeah?
Yeah.
Better, I guess?
So yeah.
Yeah. So we can have a look at app. This is, oh, again. Should I do it for every buffer, I guess? Yeah. Yeah. You have some configuration for kernel. Well, you basically describe memory layout, some feature lists for every task, and priority assigned to it. So this one, this is a demo example. It has ping and pong that exchange messages. It also, one of them uses a UART, which I don't have FTDI interface to today, so we're not going to see anything on UART. It would write ping on UART, if you, in case you wonder. But there is idle task, there is Hifi task, which I'm not sure what it does. There is a Jeffe task, which is, I'm being told this really jefe because it's Spanish, which means boss, chef, yeah. So it is a kind of instrumentation task for humility to provide endpoint implementation for some of the commands. So let us flash the board. It the build system, because it's a cross-build, cross-compilation system, it uses some own extensions for cargo. I'm not sure how it works. I'm not a Rust guy. I'm just passing by, and it builds and flashes the board right away. It's not really spectacular. There's nothing really to show on it, but we can attach with, yeah, you had a question?
No, I got my answer in your comment. It uploaded via the ST link.
Yeah, it uses the vendor-specific programming tool in the end, or OpenOCD or something like that. But I think the actual flashing is controlled by humility itself. So this build script invokes humility, the debugging process, which, as I said, more than just debugger in the system. So humility, yeah. It can be run in batch mode, but by specifying command from command line. But I prefer to invoke a REPL, and you can get a list of the commands here. It's plenty of commands. Some of them, as I mentioned, really quite specific to certain boards, and yeah, there because probably there wasn't a better place to put them. But let me see, we can probe the board. tells us some information about architecture and whatever is configured on it. We can see the memory map. That's where our tasks landed. So you see some segment sizes are 8 kilobyte, which is probably flash partition, and some of them for the same task is 1 or 2 kilobyte, which are assigned for RAM. It has a certain, if I have to remember it, let me see. It has we can do registers. It's just a register dump. It can also show you a stack that's currently been I guess here. But that's on its own, it's not useful if you're not looking at which specific tasks in which specific state or no. Tasks, right? So you see our tasks. You have priority, we have generation, and you see ping. It has generations increased. It means that it's actually dying, you know. Getting killed and getting restarted. And incredibly enough, we have a bug in Rust code, so that's why generations comes useful. So let us try to have a look what is happening. I don't quite remember how I did before look up the variables. Yeah. I think that was. So we have some system variables, and one of them is exceptions. We can also tell Chefe to put a hold on ping. Ping is our failing task. Put a hold on it when it fails next time instead of restarting it. Right? So yeah, we have mem fault. So we can try to confirm it in the, which variable was that? Exceptions. Yeah, it tries to access null address. Not a typical bug for Rust, you know. But we got to have a look then in our task. Oh God. Yeah. Anyone here understands Rust? Yeah, I'm looking for fault, and he says something with fault. So what happens here? Fault every 100. Yeah, it does fault. So what it does, for some reason, it has a null rate function and it has division by zero function. And what it does, apparently, it tries one of them or another. And we get in our memory fault from here. So let's try to just remove that bit. right?
You just don't want to increase the fault every or fault sooner. It's kind of an incremental fix.
We'll see.
Then you get more money.
We'll see. Let us see if it's gonna build this time. Oh, there was a warning. Yeah.
Unused.
Unused, okay. So we attach now. Okay. See, and generation counter is not increasing. We fixed our bug using amazing debugger technique. No, but that's, I guess, how it works more or less with the hubris and humility combination. I think it's still humility at least has provision to use GDB if you prefer GDB. But since it's Rust system done by Rust guys on both ends on system and debugger, I think it's this one is much more better debugging tool for most tasks. They mentioned that they theoretically that it's theoretically possible to have tasks implemented in other languages like C or assembly, and then maybe it's a different story, but so far it's only Rust code I see in the system. It's if we conclude the nice tidy system, and for the type of the work they do, which matches very well to finished state machine, which some event-driven system. It's really a good abstraction. I'm not sure if you have some other problem domain which maps to it less natural poorly, and if you have some really complex state machine, how all this preemption thing with blocking notifications gonna work if you scale up to say many dozens of tasks. But probably you're kind of working with the wrong tool there. You don't need microcontroller than if you want a full-fledged operating system with many different tasks. And anyway, on those memory and resources are limited, so there isn't really that much room for that. So yeah, it was compared to other systems I've seen before, like FreeRTOS and others like that. It's a high novelty factor, I would say. So that was about it I had to say about Hubris.
Is it alive anywhere in the wild, like anywhere in production?
Well, they use the Oxide, the vendor. They use it in production on their products for this. Yeah, for this IPMI type controllers. The explanation was they tried to find already some pre-existing solutions, but there wasn't anything that was specifically secure, easy, and open source, and all that combination together. So naturally, they wrote an operating system.
And this one, it's strictly single-threaded, right?
Hmm?
It's strictly single-threaded, right? Or
yeah. Well, it's not threaded at all. Let's say it. It's, there are no threads. It's the tasks preempt each other. Like if you have notifications, you can sort of use notifications to generate preemption event
but
for
you
the
can't
task.
have concurrent tasks.
Huh?
You can't have concurrent tasks running at the same time.
I think you can, but if it gotta be really hacky, you'll have to do it programmatically, sort of in via IPC mechanism it has.
Yeah, the STM usually has multiple Is like Heffa the scheduler? Is that who?
That's a mystery for me. I think humility has help hifi. It has a hifi command, so it's actually operation that writes on release, write on release. Timeout, print, read data. Hif functions. What is hif? I don't know. So
Fair enough.
yeah. So something to do with leases and memory. Looking from help command description. Yeah. So now I let Knut Arild preempt me.